All right, day 0. Let's take a look at this first drawing and go ahead and figure out what do you see. Just as a reminder, any time during this video, you can always pause and rewind and not miss anything. All right, so we can see that we go from one arrangement to another arrangement to another arrangement. And each time we add 4 squares. And we see that we have the beginning, 1 minute later, 2 minutes later. So one thing you could have said is the number of squares increase by 4 after each minute. So if we take a look at this table, at the beginning we have 5 squares. After the first minute, 9 squares. After the second minute, 13 squares. And each time the number of squares increase by 4. If we continue that pattern, add 4, add 4, add 4. Just as a quick comment, in terms of rate, what sounds better? If we increase 4 squares per minute, or in 1 minute we increased 4 squares. And I'd say that this sounds better. So if we talk about 4 squares per 1 minute, the squares is the y, and the time is the x. And so rate looks like it's the change in y over the change in x. And that might sound familiar. We go ahead and plot these points. 1 box per square in the y direction, but 2 boxes per minute in the x direction. After 0 at the beginning, we have 5 boxes. 1 minute, we have 9, 13, 17. If we adjusted the scale, we can get the other 2 numbers in, but I don't think that's important. Next question. Should I connect the dots? In other words, after 30 seconds, should I say there are 7 squares? I don't think we're going to have an arrangement with 7 squares. And so these points are distinct or discrete. Distinct, a word you know. Discrete, maybe a word we don't use as often. This idea of the rate being the same sounds to me like slope, like we talked about before. And the beginning, if you look at it as a graph, is the y-intercept. And so if I say that the slope is 4 squares every minute, and we start at the 5th square, we can have this equation. Since there seems to be a constant rate of change, it's linear, and so I can use this equation. But because of the situation, we would only want to plug in whole numbers. Remember, the whole numbers start with the whole, 0. Let's continue on with this idea. The sequence is linear if the rate of change, or our slope, is constant. And that's a constant difference, where we can subtract, 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 and the answer doesn't change. You guys go ahead and fill in these sequences and see if you can see the pattern. So we can see here 10, 10, 10, 10, 10, 70, and 80. The pattern is we add 10, and it's constant, and so yes, it is linear. And if we go ahead and look at sequence 2, we can see divide by 3, divide by 3, divide by 3, divide by 3, again and again. Our pattern is divide by 3. But remember, when you were taught division, it's the same thing as multiplying by the reciprocal. So you could have said either one. And is this linear? Well, whoever wrote this was wrong. The answer is no. We are not adding the same thing each time. There is a pattern, but it's not linear. Okay, let's see. Add 1, add 2, add 4, add 8, add 16. What's the pattern? Double the y values each time. Double, 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 double. And again, it's not constant, so it is not linear. Here, we're subtracting 7, subtracting 7, subtracting 7, subtracting 7, subtracting 7. And so if I continue the pattern, subtract 7, subtract 7. So the pattern is we subtract 7, but remember subtraction is the same thing as adding the opposite. So we are adding a constant, and yes, it is linear. This pattern is a little bit different. Add 1, add 3, add 5. So we add 7 and add 9. You might say we're adding odds. I say we add 2 more each time than the previous one, and no, it is not linear.